Okay, so now we're recording. And let me get the participants back. And let's see, Adam and Mary and Patrick are here. Okay, why don't we get started? I think we got a pretty good quorum. I guess thanks to everybody for coming on behalf of all the SIMA co-leads who organized this and everybody working on it. We wanted to just provide another update on what's happening with SIMA, the System for Integrated Modeling of the Atmosphere. And I got to advance the slide. So is that advancing now? Everybody see that? Somebody give me a thumbs up. Thumbs up, thank you. What we want to do for an agenda is provide just a background update and kind of project status of where we are. We'll talk quite a bit about applications for where we are in SIMA version 1, and I'll describe what SIMA version 1 is. I'm going to mute Roy. If he doesn't mute himself in a minute, if I can find him. There we go. Okay. And then talk about next steps, and we'll hopefully have time for discussion. So for those of you who don't know, and I think we talked about this last time, but Jordan Powers in M3 is actually the SIMA software engineering project manager who's been working with us and doing a fantastic job in helping coordinate across labs and sort of actually try to build a culture of software engineering that's working across laboratories at NCAR, which I think is going to be really powerful for us going forward. Myself, Andrew Gettleman, Mary Barth, Hanli Liu, and Bill Skamrock are the co-leads for the SIMA project, the science co-leads. And there are many SIMA collaborators, both internal and external. I've tried to credit those people in this presentation, and some of them are actually going to be speaking. But there's a whole lot of people behind the scenes that have been doing a lot of this work. And so our apologies in advance if we don't call out everything that we should be calling out here. So Mary, Bill, or Hanli, do you want to say anything? Okay. So as most of you know, the SIMA's this effort is an effort to unify NCAR-based community atmospheric modeling across weather, climate, chemistry, and geospace. It was developed and defined with the community. We have a vision that resulted from a workshop in June of 2020 that many of you were at. The SIMA vision is a configurable system. It is not a single model. It's sometimes called a model, but just like something like WRF or CESM, there are lots of different configurations of that model. And so SIMA has a lot of different possible configurations. These are atmospheric configurations within an Earth system model, and that Earth system model framework is CESM and SEAM, which is the infrastructure for it. Our target has been a minimal set of interoperable components, where those components, in this sense, we mean internal to the atmosphere model. So the physical, chemical, upper atmospheric parameterizations, and then the dynamical cores. We're using common infrastructure methods to share and extend things like diagnostics, tutorials, and to reduce duplication of effort. And it really is a community. So thank you for being here today, and thank you for your time, and thank you for your engagement. We have something like 51 people just internally on the call, and there's an equal number of people externally who are getting more and more involved in this. So the SIMA vision, if you look on the left, this is sort of where we are now with our atmospheric modeling ecosystem in the mid-2010s, or now starting into the 2020s. We have global models for CAM, WACM-X, WACM, part of CESM. We have mesoscale models and regional models for MPAS and WRF. We have special versions of that run at higher resolution for air quality, and we get all the way down into the convective and LES scales. And the SIMA vision is actually to try to unify most of these on a firm foundation for process modeling, and put all these community models that we use together. What it looks like is something like this. SIMA is the atmospheric component inside of CESM. So if you blow up the atmosphere, and many of you have seen these slides before, there's a set of, and we'll just focus on the interoperable components in that atmosphere, recognizing that it's inside of a coupled system. We have different sets of physical and chemical parameterizations on the top. There's a physics dynamics coupling layer. There's different possibility for dynamical cores, and there's the option for data assimilation. Don't worry too much about where the data assimilation is. It's not necessarily to indicate that it's embedded inside the atmospheric model at this level. It's just a notional, basically, functionality for modifying the state of the model as we go forward based on data coming in. So if you're thinking of a climate model, such as the next version of CAM 7, the community atmosphere model, it might look something like this. This is sort of where we are now. We have the CAM physics, we have the Musica aerosol package, and we're hoping, or at least expecting, to use the spectral element dynamical core. For polar, it might be slightly different. So for the polar configuration, some of which I'll actually show today, we might have a spectral element with regional refinement over the polar regions. And again, some of the things we'll talk about today are actually coupled, but this would be the atmospheric configuration for that. For chemistry, again, some of the Musica simulations that have been done have more explicit chemistry. So I've highlighted the chemistry here, and they have regional refinement. Also, say over the United States, or focusing in on one urban region or a mega city or the region surrounding that. For geospace, they've also done a lot of work with the spectral element dynamical core. They might also be using data assimilation to reproduce, say, a particular event with a solar storm over a particular time period, but they also would add coupling to a plastosphere and thermosphere model, and there's been adding the ability to couple to a geomagnetic grid to the atmosphere model, which is important for, because those calculations are done along magnetic field lines, not so much on a latitude-longitude grid or on a Cartesian grid. And then for weather, of course, you would have something that looks more like Whorf physics with a non-hydrostatic dynamical core, such as MPAS, and that might also run either initialized and or with data assimilation in a more traditional weather or mesoscale type configuration. Again, but being a global model. Okay, so where are we with this? Well, we now have a website. There's sima.ucar.edu. There's detailed information on the configurations. There's history. As many of you know, the overarching history is a small reinvestment project that was internally funded for FY 2020 last year. That was SIMA version 0. We had a workshop towards the end of that last summer that helped define a vision going forward. There's been an additional reinvestment project this year, SIMA version 1, V1, where we've been developing more ambitious configurations across SIMA frontiers. And we also added Jordan, our software engineering project manager, to help oversee and coordinate some of these efforts on the software engineering. As a part of that, we've updated the SIMA project plan especially for SIMA version 1. This spring, we had a specific SIMA-related supercomputing award for time that happened in April for polar and geospace configurations. We also contributed and helped support the South America collaboration with some of the South America simulations that also got another NSC award. And SIMA was a big part of the recent modeling site visit team, and Mary Barth was one of the co-chairs of that effort. So thank you, Mary. And so SIMA was very well represented in that, and I think came out hopefully very favorably. We have ongoing development, and I'll talk a little bit about that. Examples of working with CAM MPAS development and getting MPAS into CAM in a non-hydrostatic core, and then MICM and Musica chemistry. We'll also talk a little bit about our SIMA version 1 configurations and applications that we're developing, and many people are involved in the following projects we're going to discuss. We're planning external outreach. We have plans for an advisory board, which will try to constitute and stand up this summer. And then as we get to the release, we're planning a workshop and tutorial, which is both for internal and external participants. And we're also planning, as you'll see, for what happens beyond September, hopefully when the reinvestment funding ends and we actually have some things to deliver on this. So some of our ongoing efforts that many of you participated in, most of the ACOM folks will be very well familiar with Musica and MICM that are moving along and integrated with SIMA. the CAM MPAS integration and testing. This is work that's been happening with a lot of work from our software engineers, Michael Duda, John Truesdale, Steve Goldhaber, and also lots of science support from both M-Cubed and CGD. We've been doing a bunch of infrastructure upgrades for CESM and SIMA behind the scenes. Some of this is happening anyway, things like UOPSI integration for new coupling architectures. Some of it is more SIMA specific, such as dealing with scaling issues and physics dynamics coupling inside of the existing infrastructure for CAM to make it more amenable to the SIMA goals. The new physics interfaces, the Common Community Physics Package, has been in development and integration both in CSM and CAM and in MPAS and WRF. That's been a lot of work happening. Again, also Dave Gill's been involved with that, and Steve Goldhaber's been involved with that, along with Jesse Nussbaumer and some of the other software engineers, Cheryl Craig on the CAM side. And there's been a bunch of work happening. Francis Vitt, Steve Goldhaber, and others, and Joe McInerney have done a bunch of work on the geomagnetic grid for WACM-X, and I think that's working quite well now. So there's some examples of that we'll show also. So these are sort of ongoing efforts behind the scenes that are not specifically focused on one particular application, but are sort of necessary and cross-cutting for everything. And you can see they sort of involve all different efforts across the institution. So I want to talk a little bit about what's happening with some things with CAM MPAS and chemistry. So Bill, if Bill's on the line and you want to jump in, there you go.
I'm here. So working with Peter Luritzen and John Truesdale, and kind of we used to be working with Brian Eaton a while back, and he retired, and Michael and others. We are at the point where we're testing MPAS effectively on 1 degree meshes, and I just want to show you just 2 quick results in terms of the speed of the computations, not so much the accuracy here, but just how we're running. And what you're seeing on the right-hand side here is a plot of the speed of various models in an aquaplanet configuration. And this is in simulated years per day, and versus the number of nodes on the x-axis there. And MPAS is these kind of aquish colors, upside down triangles. And you can see we scale pretty much with everything else until you get out to very high processor or node counts, processor counts. A lot of the work that on this, at least in the climate world, is done at this kind of 48 or 50 node mark. And as you can see, we're looking at about 25 columns per thread there, 25 columns per processor, and this is certainly well past what we typically do for weather. So we're scaling out actually better than WRF in this regard in terms of parallelization. But what this shows you is that we're pretty much where we expect it to be, and we're within the mix of all the other dicores that are sitting inside of CAM. The last thing I'll say about this is that a lot of this simulation is most of the time spent in physics, so it isn't so dicore dependent. Next slide, Andrew. Just one other result. The question is, when we go to chemistry applications, which of course for air quality work and a number of other things we want to do are important. This is looking at a certain configuration here. We're looking at about 45 columns per thread of MPAS, and we're looking at increasing the number of tracers to see how effectively well the transport schemes scale. Now here, this is time to solution, so being lower is better here. As you can see, MPAS is doing quite well, and we're scaling out to here 500 tracers. So the MPAS dicore is coming along. It's passing the test that we hoped it would. Next steps now are there's some work on for climate applications on the energy fixer. For weather applications, we're bringing in much higher resolution meshes, going down to 15, and that 15 to 3 kilometer mesh, and we hope to have that, begin testing that within the next week to few months. We're going to be running that. Back to you, Andrew.
Okay, just to take this one step further, so this is actually taking that version of it and actually running with the full CAM 6 physics suite with MPAS at climate resolution. So it's 1 degree. This is sort of for those of you in the climate world, this is a standard sort of climatological test for 5 years, run in CAM. And the blue line is the baseline CAM, the red line is CAM MPAS. And this just basically shows some of the cloud fields that we're there's differences in here. The purple is actually observations from the NASA Ceres satellites for Ceres for liquid water path and cloud fraction, but we're actually producing a reasonable climate. This is work that I've been doing with Xingying Huang. And this is just a little bit more. There's the total precipitation looks fine, and the cloud radiative effects on the bottom two, the shortwave and long wave, are actually looking pretty good as well. There's obviously some differences here. This is not unexpected. Some of this is probably a knock-on effect. There's not much difference in the clouds. This is, again, you can see those both look like a very similar planet with small differences. The differences are actually higher up, and it's probably coming from some of the dynamics. So this was a quick cut without really doing a whole lot of work on the damping at the top of the atmosphere. So these are log scales now going up to, I think these go up to about 3 millibars. And you can see we're getting differences in the upper part of the model in the jet, which is really getting into the damping layer. That then filters into the temperature, and that also affects some of the cloud simulation. So we think there's nothing really wrong here. It's just differences in how different sorts of the aspects of the die core are performing. But this is very promising for early stage. And there's no sort of showstoppers in running any of the CAM physics, at least at low resolution, using a non-hydrostatic formulation for height that we're then converting over to pressure to run the physics. And Mary, if you want to pick it up from here.
Okay, yeah, I just want to update you on some of the Musica work. So if you recall, there was a release of Musica version 0 last fall. That's CAM-CAM with the spectral element using regional refinement. And that default grid is over CONUS. And so that's about 14 kilometers over the US, one degree for the rest of the globe. And since that time, there's been a lot of work actually applying Musica version 0 to other regions. So there are other grids listed there. And then at the bottom, we just list some of the applications that we've been doing. So the original runs were done for ozone air quality and PM 2.5. We have an ASB postdoc, Winfrey Tang, looking at fire with this Musica setup. We have started using Musica version 0 over the ACLIP East Asia region for the ACLIP field campaign. A collaborator at University of Iowa, Beirut, is doing India air quality, and another ASB postdoc, OC, is looking at biomass burning over the Gulf of Guinea. And the other thing that we've started, that Simone has started, is a set of CONUS simulations over the last decade for community analysis, and so we're hoping that becomes something that the entire community can make use of, and we can push or advertise Musica version 0 a little more. Next slide. Another thing that ACOM has been working on is our model independent chemistry development. We now have a mature version of MusicBox, the box model version of MICM, for gas-phase chemistry. This one thing that does not do, though, is use CCPP, but we are in ongoing discussions for getting MusicBox and CCPP working with contemporary software. I wanted to note that our MusicBox has executables with Docker, HTML, command line, and module executables. And shown in the figure is a screenshot of using it on the web, where we can dictate reactions or species. We can look at what the flow of reactions are for a particular species. And so we're now, next steps are implementing heterogeneous chemistry and starting to design interfaces for the aerosol processes. And I think I'd be done.
Thanks, Mary. So what we're doing with a lot of this back-end work is we're actually gearing up for some SIMA v1 applications. And as it'll explain, the goal is to actually get these out to the community sometime in 2021, hopefully in the late summer or fall. And these are in a bunch of different areas. So we're going to run through some of this, and some of the people involved are going to actually talk about these different areas that we have for for SIMA, which is weather, chemistry, climate, geospace, and polar are sort of the main areas. And just to focus in on this, so for coupled weather simulations, this is an example of an MPAS grid for the precip project happening in East Asia, which is 15 kilometers in the outer part of that region, telescoping down to 3 kilometers on the inner part. So this would be actually done with a coupled ocean and initialized. So that's one set of configurations that we're looking at. And the fallback is we may not quite get there. We may not quite get there to release this coupled. We may have an uncoupled version. We have to still do some testing this summer. For regional air pollution, 3 kilometer refined mesh over Asia with chemistry initialized. So this is an MPAS version, as Mary said, for ACLIP. They're already looking at a 14 kilometer spectral element refined mesh version, which is similar and might also get released out there if it's ready. For climate, there's been some interesting work. This is showing a couple things. So in addition to the CONUS grid that Mary showed, there's also an MPAS grid for that with the MPAS non-hydrostatic dynamical core. Colin Zarzicki's been looking at this and running it. He's at Penn State over the United States. We've also been looking at South America, eventually setting up an MPAS grid, which is on the right. And Patrick Callahan's been doing a bunch of work on a South America grid with the spectral element, which is shown on the lower left. And Patrick, I don't know if you want to talk about some of these very cool slides.
Yeah, so with the South American refinement, is actually, as many people know, is actually a set of refinement grids from 100 kilometers down to 6 kilometers, which have been used as a use case for streamlining and simplifying the workflow in creating, using, and validating variable resolution grids, and also for assessing the fidelity of higher resolution simulations with inner comparisons with WRF and with the future MPAS refinement runs. And I'll be talking more in detail about this, that aspect of these grids next week. And so shown here are preliminary results from the 8-month simulations from just getting everything running. And so these are the December monthly precipitation values. It started in June, so this is a little ways into the simulation. And so we show here the 100 kilometer, 25 kilometer, and 12 kilometer precipitation values, which you can see is, as the resolution increases, more structure emerges, and you get more localized and intense precipitation events that occur. These are for there's also 2 configurations. One is for the standard 32 level refinement, and then there's also a 70 level configuration in which it maintains the same height or same model top as the 32 level, but additional levels are added to align with the WRF simulations, which are going to be used for the inner comparisons here. So for the 6 kilometer run, they were expensive, so we only have 1 month. So this is the first month, so it kind of has the spin up effects in there as well. So on the left is the result for the 32 level configuration, and on the right is for the higher resolution 70 level configuration. And these are for June. And, so similarly, you can see that, much more structure emerges as you increase the resolution. So back to you.
Thanks, Patrick. That's very cool. So taking that a step further, we've also have a project that's a funded NSF project, and actually the PI is Dave Randall at Colorado State University. 2 of the people involved are Xingying Huang and Miles Curry here at NCAR, along with the co-Is Rich Loft, myself, and Bill Skamrock. And this is called Earthworks, and this is designed to build a global 4 kilometer version of CESM using the MPAS non-hydrostatic dynamical core. So this is a sample that Falco Jute did a few years ago, the sort of 4 kilometer diamond simulations with MPAS. We're aiming to reproduce something similar, but in a fully coupled Earth system model. That's just started in the last year. And so part of our CAM MPAS developments that we showed are feeding into this project. And the things we're learning also from the spectral element, the hydrostatic things that Patrick showed are going to feed into this as we go forward in the future. Han Lee, do you want to talk about some of the applications for coupled space weather?
Sure. So the last year, or this phase, we've been focusing on 2 things. One is the a new SE die core, working with Peter Lorenzen and Francis, working on the species dependence of the SE die core, and that has been done and validated. The climatology looks fine compared with FV. And the other thing is the grid regrading scheme. Steve Goldhaber and Francis worked on, Andrew just mentioned. And that also is working fine. Now we put those together and starting to look at the high resolution capabilities. And this is brand new from the from Alvin, which is Cheyenne, and showing the waves structures at the stratosphere and the thermosphere and how they affect the ionosphere bubble system. So actually, the last piece, the coupling with the ionosphere, is still in work. So this ionosphere piece is from the lower resolution coupling, I think half a degree coupling. Yeah, so the next step we're working on is to couple this to a plasmasphere model at 25 kilometer global resolution, and the other thing is to for high latitude coupling, force WACMX using the high resolution Gamera output, which is a high resolution MHD code for the magnetosphere. So that's what we're working on right now. Kevin Fenn, project scientist one at HAO, is working with us on that. Back to you, Andrew.
Thanks, Hunley. Last but not least, I've also been working on polar prediction. So this is basically taking, again, these refined mesh grids, this one was with spectral element, and refine it over the Arctic, and also to focus in on Greenland. And this is actually in a coupled framework. So it's coupled to the surface, it's coupled to an ice sheet model, and it can also be coupled to the ocean and the sea ice. This is work that Adam Harrington has been moving forward. And Adam, you want to talk about this a little bit?
Yeah, sure. So there's about 3 grids cover the polar regions. That laggy animation in the previous slide is a 1/4 degree refinement over to Arctic, 1 degree elsewhere. And that grid we're actually going to be taking to, right now I'm working on coupling it with a 1 degree pop ocean, and we're spinning up a PI control to do climate projections over the historical and into the future. The grid you're looking at now is it's called the Arctic Grist grid. It's 1/4 degree Arctic refinement, but 1/8 degree refinement over Greenland. And so I had completed some 20-year simulations with this grid, and I put together a really cool visualization with Matt Ream from Sizzle. And we actually, here, I'll put the, so you guys have
the links right there.
Can
put
you
it in the chat.
Well, here, I'll tell you what, though.
You can put it in the chat. There you go.
I put a tweet in the chat. This is my first tweet. We laundered it through the CGD account. So you can look at that in your off time.
I didn't do the video because it was going to be pretty laggy and low resolution on the Google Meet. This looks much more impressive on the Google Meet.
There you go. The visualization can be like a homework. You just watch it on your time off. But it's really cool. I worked hard with Matt to make sure that the model topography is what is being shown instead of some random rendered topography. And so it really shows the increase in resolution into the refinement zone. And then there's 2 different chapters here shown from the visualization. The first one just is a snapshot of the lowest model level streamlines, and on the southeast coast, you tend to get these acceleration down the steep slopes that are tentatively, I'm calling them katabatic winds that we're able to resolve, which is really interesting. And then on the right really is showing how we're leveraging the high resolution in order to increase our ability to simulate the surface mass balance of the Greenland ice sheet. And so the red is a snapshot of melting rates at a particular day, and you can see the ablation zones are very narrow, and so the high resolution is needed to capture that, and we've done a pretty good job with that. I'll be talking more about all the work that we're doing with these grids next week in the SIMA talks.
That's the cross working group session at CESM on, I think it's Tuesday afternoon or something.
Yeah, right, exactly. So a little bit more about these cool 8th degree runs, and then more about coupling the 1/4 degree Arctic to the ocean. So with that, I'll pass it back to you, Andrew.
Great, thanks, Adam. Thanks to everybody. So you can see there's a lot going on, and we're actually moving towards getting versions of this out for the community, which I'll talk more about. So what does that mean, getting them out to the community? Well, the goal is to deliver these configurations, and the way this is going to happen is as configurations, or they're called component sets inside of CESM, with appropriate sign-off for the people leading these applications that they're ready to go. If they're not, we can always hold them back. So CSM is planning on a release in the late summer or fall. It'll be CSM 2.3, and we'll include some of these configurations with a SIMA atmosphere in the name. These are for climate. We have refined mesh grids, probably also a global uniform CAM MPAS grid, CAM MPAS, some of the weather simulations, hopefully from 3 to 15 kilometers. Chemistry, some of those above grids with chemistry, as Mary was talking about, and then also the polar simulations that Adam was talking about, and some of the work that Han Lee was talking about in its early phases will be released. So this is development support, which in the CSM parlance means it'll run on supported machines with the right data sets and grids to sort of set up, but we haven't really done science validation or support for specific answers yet. And of course, if people need to write this up before we release it to the community, then obviously we can hold off on these releases to make sure that people have time to actually get this documented and get their science out and get credit for it before we do that. So I guess the question is, when can I use SIMA? So there's a couple answers to that question, particularly for this internal group. Internal, external friendly users, if you see something interesting, ask us or ask one of the application leads that have been talking. As you can see, there's many people already using SIMA, and we have computer time, and we're able to help coordinate and work on the infrastructure. Ask us what configurations are possible. We've had a number of discussions with groups on atmospheric rivers, on the water cycle. The more help, the better. The more interest, the better. The more people testing things and interested in working with this system, the better. The other option is you can wait for more stable configurations sometime in the fall. And as we said, there'll be a tutorial and workshop, particularly to follow the release. And that'll be designed so that if you had no experience with running the CESM infrastructure that contains this, hopefully the cases will be simple enough to get everybody up to speed pretty quickly on that. And I'm sure that will be done in a virtual way, and we'll record it. And it'll be available with some exercises as well that should work on our machines. So just finishing up a few minutes, almost done with the next steps. As many of you may have heard, there is no more dedicated reinvestment funding beyond September, beyond the end of this fiscal year for anybody, and that includes SIMA. We are working with the associate directors, the lab directors via the annual budget review process for next year to continue a lot of this funding support. And we're looking at continued funds for our coordination, both the program manager for the software engineering and adding a part-time community liaison to help get some of these applications out there and help people use them. We are hoping to continue the infrastructure development for the CCPP regridding and chemistry. We also, now that we've got a lot of SIMA configurations, we're going to start preparing, and there'll be plenty of analysis of those, both what you've seen today with chemistry, geospace, weather, and climate. We're also going to start, we hope, coordinating development of SIMA-related diagnostics and integration with the observations now that we actually have a lot of different configurations happening. We've also talked with some of you about exploring first steps for data assimilation with SIMA. Both we know what the infrastructure requirements are, and we're starting to build toward those, along with potentially some test cases for doing DA-type experiments and initialization, not just initialization, but actually simulation with these configurations inside of CESM or using CESM. And then for geospace, as Han Lee said, working to improve ionosphere coupling, and there'll also be some efforts to start on the deep atmospheric version of a dynamical core, probably working with MPAS. So a lot of these things are likely to happen because they're aligned with existing science goals that are not just SIMA. So SIMA is not some extra thing. It's sort of we've always conceived of it as being a grassroots effort, and it's the science we feel we need to do anyway, just in a more coordinated way, and that's where we're trying to add value. But that enables us to do this through the regular programs, because this aligns with a lot of our other priorities and other things that are in the strategic plan, the program operating plans. So we're hopeful that we will continue at some level with this and potentially get even more dedicated money as we move forward. So this is sort of opening it up now. This is kind of the last slide for feedback. We're interested in people's comments on or questions about these applications. What's interesting? Would you use them? Do you want early access? What do you see? And then plans based on what you've seen and what you've heard. What should come next? What are the next targets for SIMA version 2? What science can be done next that we can push forward? And we're also interested in further collaborations, obviously. So internal collaborations. All of you are here. How would you like to be involved? How would you like to help? The other thing is, how can SIMA help you? And because SIMA is a big part of the NCAR strategic plan, so showing how your work links to this is a two-way benefit for everybody, I think. And it also potentially opens us up to new internal collaborations and also external collaborations. So if you know external collaborators or even internal ones who would benefit from SIMA, contact them or let us know. We're trying to reach out and talk about this at the various modeling workshops, such as the WRF workshop this week and the CSM meeting next week. But if we're missing people, let us know. If there are people that want to be engaged with this process, let us know. Pretty sure that's it. Yep. So I'm done. I don't know if any of the other co-chairs want to say anything, or if we're perfectly happy to open it up for questions. I think if we're going to do that with this group, please either put it in the chat or just hit the raise hand, which at least they've exposed now in Google Meet. It's pretty easy to find. And we can have some discussion. So Bill, or anybody else, or Mary or Hunley, I don't know if you want to say anything.
No, let's discuss.
So questions or comments? Laura, go ahead.
Thanks for the update, Andrew. I was wondering, it seems that all the examples that you showed, they all use the CAM something physics, which is fine since MPAS dynamical is implementing in CSM. I was wondering if I were to provide a conversion permitting suite based on WRF-like physics, they are all, CCPP conformant. How easy or can it be used in terms of being part of SIMA, and how would you proceed with the initialization so we can start doing actual numerical weather forecast within SIMA? And how to get involved specifically?
Yeah, no, that's a great question, Laura. I think the answer is we are in the process right now of getting the CCPP infrastructure into CAM. And once that is done, it should be possible to then take a CCPP physics suite and put it in and use it. So hopefully in the next couple months, we will be at that point and we should be able to try that. So I'm happy to work with you, and that would be a great test of the new infrastructure that enables us to do it. So it should be possible to do. We're going to be in the process of converting the CAM physics suite, and that's going to take a little bit of time. But if we have a convective permitting suite that exists in the CCPP, that should be usable in the system in relatively short order. So yeah, let's keep in touch on that.
And let me just add a little bit to that. We're going to have a convection, scale-aware convection scheme available to get to non-hydrostatic scales. So that's certainly high on our radar. I don't see us pulling in a new suite, but I do see us modifying or replacing the deep convector parameterization for these high-resolution simulations.
Yeah,
so
Bill,
we could also use parts of the suite as well. But I'm certainly willing to try it.
Okay. But that wouldn't include actual initializations for weather application, right?
So that got garbled. Could you repeat that question?
Data or ECMWF data, for instance, like we do commonly in MPAS or WRF?
So the initializations, we have been doing a lot of work on initializations. And so I think it should be, we certainly have been doing work on nudging. Yes, in the next 6 months or no, we should be able to bring in an analysis system to analysis fields to initialize the system.
Well, let me update that, Andrew. We can pull in any analysis from, for example, GFS, IFS, ERI interim, all those as initial states for the atmosphere and MPAS for running inside of CAM right now. What we don't have is the ability to initialize the land model with other analyses right now. We have to spin that up in some manner. There looks like there are a few people who figured out how to bring in parts of analyses into CLM or maybe CTSM. I think Colin Zarzicki has been playing a little bit with that, but we haven't really run down all those options yet. So short answer is yes, we can bring in any analyses for the atmosphere. It's really the land model that we're struggling with right now and trying to figure out and come up with recipes for doing that.
Okay, thank you.
So Tara, did I see you put your hand up and then it came back down? Did you have a question?
No, I hit my hand up by accident, sorry.
Okay. Go ahead, Roy.
Well, you muted him, now you have to figure out how to unmute him.
No, he has to unmute himself.
Hey, I just figured out that I was muted, sorry. Last time we met, we talked about use cases, and this time you talked about development configurations. Are those the same or slightly different?
I think they can be the same. I don't know if you think they're different.
Yeah, no, I assume that they're different. They're the same, I'm sorry, and not different. So that helps us.
Yeah, I was not intending
South America use case, and Patrick showed this nicely.
Right. I mean, you could call that a configuration, where it's a specific application of, using the regional refined mesh in a particular area. So there are also versions of that exist for the continental United States, and there's going to be others developed for the tropics to do hurricane forecasting and analysis. So they're similar types of things, and they're somewhat repeatable. Patrick will talk about a workflow, at least for the spectral element core, and there is a workflow for MPAS to create these different grids. We're trying to make that workflow as easy as possible for people.
Okay, that sounds good. Thank you.
Go ahead, Tara.
Yeah, this time I actually meant to put my hand up. So thinking back to your slide where you were talking about, next priorities and next steps and so forth, with there not being any dedicated reinvestment funding, I didn't completely wrap my brain around how we're going to fund those priorities.
Yeah, so the way that a lot of that's going to happen, I think, is because those priorities are priorities anyway, either for our own work or specific.
We lost you.
Yeah, you just cut out, Andrew.
Yeah, I think his equipment does that every few minutes. His computer just turns off his mic.
It's only him.
Yeah, we're still not hearing you, Andrew.
Yeah, he just has to reset it.
There we go. Now I have to mute. So my Bluetooth decides in the middle of every meeting, it decides it wants to cut out and then come back. And of course, when Google Meet does that, it brings you back in muted. So sorry about that. At least I switch my mouse from being Bluetooth so I have some control over the machine when it happens now. So the answer is, Tara, that a lot of this is happening on other projects, basically. So, for example, Earthworks is a funded project to do development of a high-resolution non-hydrostatic configuration of CESM. MICM and Musica has support from both external projects and internal projects, and we're committed to do a lot of this development because it matches our science. So one of the things that makes SIMA sustainable is that it is grassroots, and we've tried to keep it going in directions that enables the science we want to do, because that makes it sustainable, and that's, I think, the big benefit. So does that kind of answer the question? It doesn't enable us to move as fast as we like, and it also doesn't enable us to make as many connections as we like, particularly like to entities like RAL that are mostly soft funded, where we would need actually dedicated money to actually make those connections work. So that's the difficulty, but the opportunity is we're not dead in the water when we lose all of our dedicated funding. Does that answer the question?
It does, and I still, so I think I still can't really wrap my brain around how, you know, I can really actively engage with this activity, because all of my funding goes in other directions other than the little slim bit of NCAR base funding that we get. So it sounds like I need to make a pitch to the RAL management that our DTC NCAR base funding is dedicated towards SIMA or something like that for the next couple of years, so that we can actually make progress on this. And I don't know whether that's going to work or not, but thanks for clarifying.
Well, let's talk about it, because I'd be happy to try to make sure that that happens more, and talk to Bill Mahoney and others about, you know, seeing what we can do. And again, we've worked with the ADs, and Bill's been part of those discussions to try to make sure that if we can do this, it'll happen. And we're also hoping that if we get, you know, part of the reason for pushing configurations forward in this phase is we think if we get the model out there, it's the field of dreams approach. If you build it, they will come. And NSF and NCAR are not going to commit money to SIMA to do the things that we're talking about because we want to, or we ask the director, or even Everett asks NSF. It's going to happen when people write proposals that say SIMA on to NSF. So we're hoping in the next year that this will unlock some of, with getting the model out there, it'll unlock some of this.
Yeah. Okay. Thanks.
Thank you. Other questions or comments? I didn't see if there was anything in the chat. I think most of those questions got answered, right? Yeah, Rich's questions got answered. So. You have another question, Tara?
I do. So talking about the community liaison, what are you thinking of? What are you looking for with regards to that particular avenue?
I guess
if you can find the funding to do it.
Yeah, if we can find the funding to do it, I guess the model is on the community support that's happened for WRF and CESM, where there have been designated people to help people use the model and to work on configurations and to sort of help get the model out there and facilitate use. So that role sort of depends on if the funding comes in and how we want to finally define it. And because it's a half-time position, it may depend on what's available, because we're not sure we can get enough money for a full position. But those roles, I think, we've seen have incredible value in somebody to just basically who knows the system. So if questions come in, they can either answer them, or they know how to find us at NCAR to hook people up with the right person to respond to their question. And it's a good way to engage with the community.
Okay.
So that's kind of what the role is designed for. That is flexible, and if people have other ideas, we're open to them. But again, it's contingent upon us getting funding, but we think now that we have configurations, that's kind of important to have.
Yeah, so just once again, out of curiosity, how are you approaching trying to get funding for that?
That's in negotiation with the ABR process with the associate
Okay.
directors. So we've written a more detailed proposal than what I showed you in bullet form to the ADs and the directorate as part of the ABR, and that's being discussed as to what's possible to fund and where this money is going to go.
Okay, thank you.
Other questions? Well, I guess if there aren't, we can give people a couple minutes back of their day. So I guess expect to hear more. Well, certainly there was information at the workshop, WARF workshop this week. There'll be more on SIMA, a special session where you'll see a little more detail on some of the things we presented by Adam and Patrick and Mary and others next week. And then stay tuned because this is going to evolve as we go forward. And we're hoping that we'll get to some of these configurations and those will be available, and we'll have another sort of workshop and tutorial for this sometime in the fall. So I don't know if any of the other co-leads wanted to say anything. Any other comments?
Well, if you have any questions that you think of after this meeting, contact any one of us and let's start discussing them. Be curious what you think of the plans that we're trying to set forth, and if we've forgotten anything or anything along those lines.
Yep. Thanks, Mary. I mean, most of this has happened in a bottom-up grassroots way, and that's how it actually gains traction. And that's how we've been moving forward on these configurations. So we're definitely open to people's ideas and people's interests across the institution. And hopefully, now that it's a big part of the strategic plan, that can help give the impetus to make it happen.
And just in case some people don't know that the SIMA session, a CSM session, will be next Tuesday from 1 to 3. And
when they're virtual, they're free. So just free up a little bit of your time and join.
And maybe the registration is still open. I don't know.
It is still, the registration is still open. I think it's open throughout the meeting. You can register Tuesday morning if you want. Okay. Well, thanks very much for your time. Thanks for coming. Thanks for your interest. And have a good rest of your afternoon.
Bye.
Thanks, Andrew.